I'm Minky, and today I talk about my paper with Aram from Iwa University and Takashi from Entity and Kyoto University. Thank you for attending here. Okay, today I basically talking about the generic limitation of generic quantum algorithm for solving the discrete logarithm problem. But always quantum is a little annoying, so let's think about just limitation of generic algorithm and just forget about this discrete logarithm as well. Then the this kind of thing, generic algorithm or generic low bound, usually deal with the so-called generic algorithm, which just use the ideal functionality of a structure, function, whatever. For example, if we are thinking about the generic group, the algorithm submit two group elements and only obtain their operation, group operation. So, and do not care about the encoding of group, for example. Yeah. So it's called something like generic algorithms. And yeah, if we can identify the limitation of generic algorithm, it's kind of identify the best possible security of the ideal functionality, like a hash function, generic discrete logarithm, or whatever. For example, if we are talking about the hash function, random oracle model says that the random oracle model is the idealization of a hash function. And in this model, we can say that, okay, function inversion is sufficiently hard and it requires the to invert a function, it requires n queries to the function where n is the size of domain. And for the discrete logarithm problem, it requires a scalar G group operation where, G is the size of group. And we have a nice heuristic belief. For example, random oracle heuristic says that our best hash construction gives like a random oracle. And kind of, many people believe that elliptic curves are sufficiently hard, so we cannot extract anything uh, about the encoding, and we only can operate group operation. Of course, there is something others, but basically, it's kind of good belief. So let's get back to the quantum. Okay, so it's pretty much the same. The quantum general algorithm just says that, okay, this algorithm does not care about the implementation of the group structure or hash function, whatever. And using this, we can identify the best possible post-quantum or quantum security of the something. And we will allow the quantum access to the oracle, which I will clarify later. So if we are talking about the oracle model, for example, quantum random oracle model, which idealize the quantum accessible hash function, it's a quite successful. So we have a tight low bound for the function inversion, which matches to the globalist algorithm, and collision finding, which matches to the PhD quantum collision finding algorithm, and much more. But what about the discrete logarithm problem? Yeah, we all know about this problem given the group element, given a cyclic group, let's say it's a prime order, and given a problem instance y, which is equal to x, we want to find x. In the classical setting, as I said, in the general group model, we need to make a scalar group operation, and it's, as far as we know, it's almost the same in the elliptic curve discrete logarithm. And in the quantum setting, Peter Shor comes in and he break our roof. He give a quantum polynomial time algorithm for the discrete logarithm problem. And its complexity is the square of the logarithmic of group size. And if we count the number of group operation, it's just logarithmic G. And our result just says that it's kind of optimal. Let's say, okay, if we are thinking about the quantum discrete logarithm algorithm, which only access the group of elements as a generic way, let's say it's in the quantum generic group oracle model, then it requires the logarithmic number of operation to invert to find the discrete logarithm. So shortest algorithm is generically optimal. But if you attend the best paper talk, it's a little complicated because they kind of improved the shortest algorithm. It's confusing, but yeah, I will talk about it shortly. Anyway, what is the implication of this work? Yeah, current best estimation, not a best one, but recent estimation of the shortest algorithm says that if we have a super nice quantum computer and its time complexity somewhat similar to what we have, and we have a super large quantum computer like a tens million physical qubit and assuming much more, we can solve the elliptic group discrete logarithm problem, RSA 2048 or something like that, in just less than 1 day. So regarding this, our bound says that, okay, if there is no algorithmic and no super brand new idea comes in, and we only observe, okay, yeah. If there is no super new idea, Shor's algorithm is almost optimal, so this estimation is kind of optimal, kind of good. So we can confident that this estimation is good, and okay, we can conclude that we have plenty of time to change our quantum weak cryptography to post-quantum one. Actually, when we upload the first draft, there was no super nice attack which use the non-generic things. But the problem is, after 1 month, like upload a new paper with a brand new idea. And yeah, it's a time complexity, so just n to the 1.5, which is faster than n to the 2, and use a brand new idea. It's very complicated and our life very bad. Yeah, after inspecting the paper, oh yeah, it indeed has a very new idea, which is small multiplication is very fast. 2 times 3. Yeah, for example, 2 times 3 is basically group operation, right? But it's very easy and it's very fast. Like its basic idea is just using this kind of operation quite many times. So it means we can see the table in in the circuit complexity, 2 times 3 is super easy. But in our quantum generic group model, oh no, 2 times 3 is super hard as all the other group operation. So it's not a contradiction and it's a kind of orthogonal. And if you are thinking about the elliptic curve discrete logarithm problem, there is no that kind of small group elements. So there is no super fast group operation. So for the discrete logarithm problem, I mean elliptic curve, our low bound is pretty good. Okay, this is the comparison. Yeah, it's orthogonal and both are good, believe me. Yeah, okay, it's a kind of implication. Let me talk about the technical detail a little. Okay, let me introduce the quantum generic group model. Recall the generic group model. Probably you know about the SOUPS group model, SOUPS generic group model, but let's focus on the Morse model. In this model, every group elements are given as a label, and we can access them only using the oracle. Like if we can submit 2 group elements and compute the group operation, and we can check the equality. If you want to extend it to the quantum setting, we probably need this kind of operation. I mean, we need to compute this kind of operation currently. So actually definition is pretty complicated like this. We basically store every global elements in a quantum black box register, and we access them by submitting their indices with some auxiliary inputs. And this is the quantum group operation we call. And in the quantum generic group model, we count this number of discourse. And of course, we extend the quantum equality agree, but we omit this one in this talk. Okay, yeah, for testing, for checking the notations, we will review the Schwarz algorithm and the quantum general model. It's a pretty simple if we write this. Yeah, we first apply the quantum Fourier transformation and apply some many group operation and apply inverse and measure. That's it. And the quantum group, group elements are stored here, the black box register D, and group operation only applied here. And there are some other elements which we don't care in the quantum generic group model. So the quantum group operation comes only in this register, especially just for comparing this one. And comparing this one only requires a logarithmic number of group operation because we can use the binary representation like this. It's an easy one. So that's it. Yeah, we can interpret Schwarz algorithm as a generic algorithm, and its quantum group operation complexity is just logarithmic. So how to prove that it's optimal? Actually, proof is nowadays very simple. We just simulate the quantum generic group algorithm in the classical generic group model, and then just apply the classical lower bounds of a square root G. Yeah, I'll caveat this. Actually, this simulation is kind of quantum, but the group operations are all done in classical manner. And this classical generic group lower bounds applies to this situation. So anyway, yeah, if we do everything right, then, okay, usually classical simulation of quantum algorithm incurs exponential blow up. So we can think Q quantum group operation algorithm might be simulated by just the exponential number of a classical group operation. And classical law one says that we should have this one. If we take the logarithm both sides, we have this. That's it. It's pretty simple. Of course, the actual proof is a little complicated, but yeah. So how to simulate the quantum generic algorithm in a classical generic group model? It's also not that hard. If we do not make any quantum group operation query, then we have only initial instance like identity and generator and the problem instance. That's it. So if we do not make any quantum group operation, what do we need these three? What if we make one more query? One query, then we only make the global element register only have this kind of thing. The first three was existing initially, and G square can be computed by G times C, and so on and so on. And they are all can be represented by G to the A, Y to the B, where A and B are quite small, 2, less than 2. We can apply this idea more and more. So inductively, we can show that after K's quantum group operation query, the group elements appear in the algorithms are of the form like this. G to the A, Y to the B, where A and B's are smaller than 2 to the K. So the classical simulations go like this. Just ignore everything and prepare this thing. It requires just the exponential classical group operation and simulate the overall quantum state of the quantum generic algorithm. Actually, it's not that trivial, but yeah, it can be done only using this one and the other non-group operations. So it completes the proof. Okay, actually, there are some caveats and some complicated things. Yeah, as I said, Schwarz algorithms are optimal because we have a logarithmic lower bound. But actually, for running Schwarz algorithm, we need to do some classical preprocessing to compute G to the A, Y to the B. But it already requires logarithmic number of classical queries. So it's a little strange, and yeah, as you see in the proof, it's a kind of trivial. So to complement, this one is the one problem, and actually we can do something better by computing much large classical computation, pre-computation. Then the quantum group operations is reduced. So this is the summary of the quantum algorithm. The thing is, we actually show that if we consider the classical pre-processing, then we can show that these things are optimal. And yeah, there is something more about the quantum randombox memory, but yeah, anyway, yeah, we can show that these are actually optimal if we consider the pre-processing model. So in summary, our research shows that Shor's discrete logarithm algorithm is optimal in the quantum generic group model, and we have a quite variation low bound which show everything's are optimal. And we actually have something more like I only said that classical pre-processing, but our actual result include the classical quantum hybrid algorithms like one small classical algorithm, quantum algorithm, classical quantum. Yeah, we also cover that kind of thing, and yeah, we also give a multiple discrete logarithm quantum algorithm, and it's with the strong quantum Ormelin conjecture appeared from a fake context. Yeah. And yeah, that's it. There's the follow-ups and related work and open question. Yeah, actually our low bounds have some gap in the constant. So can we get a tight low bound? Yeah, I have some work about it. And can you show the low bound for multiple discrete log, or can you say something about the factoring in a generic way? Yeah, I'm trying to do so. And yeah, quantum generic group action is a quite interesting question. For example, can we give any generic low bound for the group action discrete log? Or what about the non-abelian hidden subgroup problem? Actually, the discussion about this is a little complicated, and we can find more discussion in my paper. Yeah, and another question is probably Leggett's variant. Yeah, can you say something about it? Probably not, because yeah, Leggett's algorithm actually, quantum running time of Leggett's algorithm can be reduced to linear if LW is easy. So proving something about it requires assuming that LW is hard, which is very, I don't know. Anyway, thank you for listening.
Thank you. We have time for one quick question. Questions for the speaker? Yeah.
Hi, thanks for the talk. You mentioned that the reason why the Regev trick works is because in general, the group operations are hard, but then if you find very specific small multiplications is easy. I'm not an elliptic curve person, but I know that sometimes one designs elliptic curves and chooses like a base point or a generator that has like a small representative. I think like curve 25519 has like X coordinate 9 as the generator. Do you think this is the kind of thing that could fall into this kind of trick?
Actually, I don't know. I'm not familiar with the elliptic curve thing, and I only discuss people's a little. I'm not sure they are also familiar with elliptic curves. So our conclusion is, probably we don't know about it. We don't have small elements probably, so we don't know. If we can find like a variant for the elliptic curve, then it's super great. I think it's an open problem. Thank you.
Thank you.
Okay, let's thank the speaker again. Now we go with Marcel. Yes. Great. So our second paper of this session is quantum lattice enumeration in limited depth, and it will be presented by Marcel. Marcel, please, the floor is yours.
Okay, oops, can't lose my shoes. All right. Nope, we're going to go back. Let me go further back. There we are. Okay, so most of us are probably convinced that large scalable quantum computers pose a significant threat for cryptography and might be able to speed up all kinds of quantum algorithms and possibly attacks. But when it comes to the cost of implementing such an attack, it is often not clear what this exactly is. And so it is kind of important to explore the quantum speed up that individual algorithms can achieve in a concrete setting. So I'm Marcel Teipelt. I'm currently finishing up my PhD at the Castell Research Group in Germany. And over the past, let's say, year, I've been working with Nina Bindig, Xavier Bonneter, and Fernando Villa, who's also here, to explore exactly this in the setting of quantum enumeration. Okay, so why do we look at quantum enumeration? Well, lattice problems have been very popular in the past years. Of course, currently 3 out of 4, I guess at the moment, only 2 out of 3 of the NIST post-quantum standards are based on lattice assumptions. And whoever was at the World Talk yesterday also learned that lattice assumptions are well crucial for many of the advanced cryptographic constructions. Now, when we look at lattice assumptions, we also need to look at attacks. And if you actually look at the leading cost of the state-of-the-art attacks, then the leading cost of these is usually the cost to implement the shortest vector problem solver. Now, such a shortest vector problem solver can be implemented in multiple ways. One way is, for example, lattice sieving, which has been analyzed before. And the result of this analysis was very roughly, one can achieve a speed up only with extremely optimistic assumptions on the quantum hardware. Quantum lattice enumeration, on the other side, has been analyzed in the asymptotic setting, showing that this, an asymptotic speedup can be achieved. And there's also been some work in the unbounded quantum circuit model. But, oops. For now, it still remains somewhat unclear what the actual speedup of quantum lattice enumeration is for practical parameters. Okay, and this is what we're trying to address. So this is what we're going to do today. First, we're going to make sure that we're on the same page about the quantum cost model. Then we'll peek a little bit into how lattice enumeration works. And then we'll come to our contributions. The first of which will be a classical quantum algorithm to actually perform quantum lattice enumeration. And in the end, we'll take a look in how, into a case study on how or if quantum lattice enumeration can speed up, enumeration for Kyber. And then we have some more results on, like, let's say, the size and distribution of enumeration subtrees, but we'll not really talk about that today. Okay, so we'll start with the quantum cost model. We'll work with a quantum circuit model. It's basically very simple. We have basically qubits in horizontal lines. We have gates in, like, let's say, vertical columns. And you don't need to know anything about this. There's just 2 things you need to know, which relate to our cost matrix. And that's the first thing is we consider the G cost, which is, the number of gates in the quantum circuit. And that usually corresponds to the idea that applying a single quantum gate requires 1 classical CPU cycle. So in this example up here, we have a total number of 7 gates, so a G cost is 7. Now the second metric that we use is the T depth. The depth of the algorithm is this is a older presentation, is the number of serial gates that are applied, the largest number of, or the maximum number of gates that are applied serially on any of the qubits. And in our case, we also consider the T depth only because the T gates appear to be the most cost-intensive gate to construct a quantum computer. And then the depth also loosely corresponds to the time that is required to keep the quantum computer coherent. So that also appears to be a main hurdle when we want to construct an actual quantum computer. Now, this was also recognized by NIST, and they presented or proposed these 3 hypothetical max depth values. And the max depth value basically means, the number of gates that a quantum computer is expected to be able to run in, either the next years, the next decades, or the next millennium. So respectively to the power of 40, to the power of 64, or to the power of 96. And what that means is that any quantum algorithm that has a depth larger than any of these values will have to be cut into, individual quantum quantum algorithm or quantum computations, well, let's say the quantum state is fully collapsed after this many gates. And then, of course, if we have some kind of quantum algorithm, let's just call it quantum innovation, then the T depth of this quantum relation has to respect the max depth limit. Okay, so next we'll peek into lattice enumeration. We have a setup that we have given a lattice and a basis. The basis generates the lattice of dimension n. And in enumeration, we have given this lattice basis. We're given some bound R, and we want to find a vector B such that the length of this vector is below the bound R. And if we instantiate this bound R with the first minimum in the lattice, then enumeration basically solve the shortest vector problem. Okay, so enumeration classically basically is done by defining a depth first search on an enumeration tree. And we don't really want to look into the tree. We also don't really want to look today on how the tree is specified. There's two things that you need to know. Well, the depth first search always starts at the top node, at the root. The tree has has height equal to the dimension of the lattice. And if there's a short vector, then that's always on the last level of the tree. And if we have this tree, we can actually approximate the number of nodes in this enumeration tree using the Gaussian heuristic and the geometric series assumption. And we're not going to look into how that works. We'll just accept that that we can get this somehow. Oops. Okay. Okay, so now if we look at lattice enumeration, classically the complexity is, well, polynomial in the number of nodes of the tree, basically until the depth first search or the exhaustive search finds the short vector. And now Ashley Montanaro showed that there's also a quantum algorithm, a quantum algorithm that implements a depth first search, and that basically is a quantum random walk, which applies a quantum phase estimation to the operator W, and this operator W kind of mimics the depth first search in the tree. And now this the quantum phase estimation applies roughly square root number, also tree size times height of the tree, mainly calls to this operator W, but that only detects the existence of a vector in the tree, and then you need like an additional polynomial number of repetitions of this to actually extract the short vector. And then from this, the only thing that we have to take away is basically, well, the quantum phase estimation is the only part that's actually a quantum circuit. Everything else just a classical repetition. So if you look at our max depth limit again, then, well, the depth of the quantum relation really is only limited by the depth to compute this quantum phase estimation. Okay, and now we can take this value from before. So let's say this square root of the tree size times the height of the tree, and we can just throw in some numbers just to get an idea what the size of such a tree is and what the resulting depth would be. And well, these are very, very loosely estimated numbers. We ignore basically we would make every mathematician cry who looks at this in detail. So we just ignore a lot of things, something like the Jensen gap that we'll talk about later. We'll just take a look at what happens. So if we put in the numbers, for example, for Kuiper here, then we can see that for Kuiper 2 and Kuiper 3, the depth here is significantly larger than any of the max depth values that we have from the MIST framework. And only for Kuiper 5, we kind of reach highest possible max depth. And this can suggest that just applying this quantum phase estimation to the complete tree will not really give us a useful algorithm, or just doesn't work. Okay, so what do we do? Well, we need a new kind of classical quantum algorithm that somehow brings the depth down. Okay, and so what we do is basically we do a normal, let's say, divide and conquer, what is also used in classical parallelization. So what we suggest is we compute all the nodes of the tree, starting at the root up to some level k, and then as soon as we reach level k, we basically compute quantum relation for every node on level k, and every node, of course, has some kind of subtree associated with this, and then we can choose level k in such a way the depth of the quantum phase estimation respects our max depth limit, and possibly also such that the overall cost is reduced. Now, our argument in the paper is a little bit more complicated than this, mainly because, well, first of all, we consider lateralization with extreme pruning, which means instead of having a single tree here, we have like a hypertree that spans multiple trees generated from re-randomized bases. And we also, instead of taking a single node here, we kind of, well, collect a bunch of nodes in level K and then form a virtual subtree. But the idea is the same, and we can basically just continue with this for now. Okay, so now we want to do like, let's say, a quantum cost estimation of this. And there's a couple of things that we need to take care of. First of all, we need to find a way to quantify the size of the subtrees of the nodes rooted on level K. Second is we need to talk about the distribution of the subtrees, since we need to, well, iterate through all of them. And then the third thing is we also need to figure out how many calls to the operator W we need in our quantum phase estimation, which is basically what well, the result of Montanaro gives us. Now, I don't really want to talk about the top three, but I do want to talk about one other thing, and that is basically how we get to this square root. So what we need, well, we have the expectancy over the distribution of all of the trees, and what we need is the expectation of the square root of the tree size. But unfortunately, if you remember the first slide, what we actually get is the expectation of the tree size, and these two are clearly not the same. And in fact, we also don't really know how to compute the lower. So the best thing that we can do is, well, we know that the Jensen's inequality, and this basically tells us that the right side is upper bound for the left side. So what we do is we define something that we call the multiplicative Jensen's gap, and we say, well, 2 to the power of z times the left side is equal to the right side. And we don't know how big this value z is, but I'm telling you this because we're going to quantify our results relative to the size of this unknown gap later. And by later, I mean now. Okay, so with that, we basically continue with our case study where we look at what kind of speed up we may or may not achieve for Kyber. And here, what we basically do is we consider a primary attack on Kyber with BKZ as the lattice reduction, and then using this classical quantum algorithm as the SVP solver. And then, of course, the block size for the BKZ you can get out of the LW estimator. Sorry, this AC kills my throat. Okay. So what do we do? Well, we compute the total cost of our algorithm. That is basically the cost to do the classical pre-computation up to level K, and then the sum of, well, all quantum iterations for all trees rooted at level K, where we choose K in such a way that the depth of the quantum phase estimation respects the max depth limit. Then we take this total cost and we compare it to the total cost of running Grover's algorithm on AS, which is basically the baseline for the security levels of NIST. And now we come back to our Jensen's gap, and what you do is basically find the Jensen's gap to the power of z, such that the total cost is less or equal than that of running Grover on AS with our max depth limit respected. Okay, let's look at some results, and I need to explain this a little bit more. So up here is just a reminder for you what this multiplicative Jensen's gap is. And then the way that we quantify the size of our subtrees, we get basically multiple ways to well, let's say bound the size of these subtrees. And for now, I'll just call one of them hypothetical lower bound. And we actually call this lower bound over upper bound in our paper. And in the next slide, we'll have something that I call, well, let's say state of the art, which basically corresponds to the way that, let's say, the size of inversion trees are currently approximated in the classical setting. And then another thing to mention is, I mentioned this operator W, and which mimics the depth first search. And well, we initially went with a very conservative setting where we just say, okay, obviously this is some kind of polynomial time quantum algorithm, but we just consider a query model. So let's just see what happens if we set this to 1, which is of course extremely generous to adversary, but at least it gives us some lower bound. And then we also have something that I will call the minimal circuit, which is probably not a minimal circuit to implement this operator. In fact, it's basically just the cost to do, to quantumly do a single compute the length of the vector once and compare it with the bound. So just like some kind of circuit that is probably required to implement this, but by no means a full circuit to do this. Okay, so now we can look at some values. And then, well, let's remember the Z values that we see here are basically the Jensen gap that is required in order for the total cost to be less than that of running Grover on AS. And as I said again, we don't know what these values actually are. We can just bound the size of them that would be required to actually get a speed up. So what we see here is, for example, that for Kyber 1, the Jensen's gap that is required is relatively low. But then as soon as you switch up to Kyber 768, this is still quite low for, well, this trivial quantum operator. But as soon as we put any kind of cost for this quantum operator, it already increases significantly. And then for Kyber 1024, the Jensen gap that would be required to achieve any speed up is already super high. And well, this kind of suggests that, well, maybe it may be possible that quantumation provides some kind of a speed up, but then again, we have very generous bounds here. And well, for Kyber 768 and Kyber 1024, it's rather unlikely that quantum speed up will have any effect. Well, now we can look at the same numbers for, well, this let's say state of the art bounds for the size of the subtrees. And here you can basically see that, well, for Kyber 1020, Kyber 512, the Jensen gap that is required is already relatively big. And for, well, Kyber 768 and Kyber 1024, the Jensen gap that we would need is, well, tremendously large. And, well, that suggests that, well, at least on Kyber 768 and Kyber 1024, the quantum speed up of formation will probably have no effect. Right. So where does that leave us? Well, we have seen this Jensen gap, and we see that there's, well, the Jensen gap is basically the gap between the actual cost to run the algorithm and the expected cost, and we don't really know what this is. And well, there are some more gaps between well, these lower bounds and the actual cost, some of which is, well, the Jensen gap, the cost to implement this operator, and some more that we have in our paper. And now it would be great to get a better understanding of these properties of the trees. Yeah, with that, I'm basically at the end of my talk. You can, of course, find our ePrint here, which also has a ton of experiments in the appendix that did not have space in the crypto paper. And you can also find the code to, well, verify all of our, reproduce all of our nice tables and some really nice graphs in the paper. Okay, thank you for your attention.
We have time for one quick question. Yes, please.
Thank you for your presentation. I wonder why you you design quantum enumeration, not quantum sieve to solve SVP. And in your hybrid model, you sum the classical cost and quantum cost. I think the classical cost and quantum cost is different, but are different metrics, because classical cost is the iteration of operation, and quantum cost means the number of gates. So I wonder why do you sum the two metrics?
Okay, so the first question was, why do we use slat enumeration instead of sieving? Well, because for sieving, there's already been somebody who's analyzed that, and for enumeration, that simply wasn't there. So does that answer the first question? Okay, and the second question is, I assume, here, for computing the total cost. Yeah, okay, so you're actually right. When we compute the classical pre-computation, what we technically count is the number of nodes in the tree and not the cycles. And when we count the G cost, that technically corresponds to, well, applying a single single quantum gate. So you're right, that is actually not very precise. It's just that in a classical setting, the cost of, well, classical lattice illumination is quantified over the number of nodes in the tree. So we just kind of took that. Does that answer the question? Okay, wonderful. And of course, if you have more questions that we don't have time for, feel free to drop me a mail or.
Yeah, we are running out of time, but thank
Wonderful.
you again. Thanks again. Yes, and we are ready to go for the last paper of the session. So it's quantum randomness of the single round sponge with multiple permutations, and it's going to be presented by Joseph. Joseph, please go ahead. Thank you.
Great. Thanks, everyone. Yeah, my name is Joseph. I go by Joe, and I'm a student at University of Maryland. And this is joint work with Alex Paremba, who's at MIT. Oh, good. Okay, so just some motivation for the constructions I'll talk about. So this hash standard is SHA-3 right now, and inside of SHA-3 lives something called the sponge. And the sponge is a generic construction for taking some object that has a fixed input length and a fixed output length and produces a function that has a variable input length and maybe even a variable output length. And it's a pretty simple construction. So in this diagram that I drew, this is the sponge. Phi is a fixed input length and output length object. So there's two like equal, two wires as input, two wires are the same size as output. And if you have an output that doesn't fit inside of phi, what you do is you take first part of the inputs, you pad it with zeros, run it through phi, then XOR in more and kind of keep going, applying more applications of phi. Then at the end, you get some output at the top wire and like bottom wire, you might want to think of as like internal state. We're just going to throw it away. And so, clearly this is only a good hash function if phi satisfies some properties. So, okay, what is phi? Phi is, in most cases in the real world, like in SHA-3, the usual model of phi is that it's a permutation. So the size of the top wire is rate many bits, and then the size of the bottom wire is capacity many bits. So it acts on rate plus capacity many bits. And in most standard settings, a minimal assumption is that this permutation needs to have some public description if we can evaluate the hash function. And that means that an adversary with a quantum computer could prepare tuples that look like this, and these will be efficient. And in particular, they can evaluate the permutation forward, and they can also evaluate it in the backwards direction. And so that's like a minimal assumption for modeling adversaries. And actually, it's pretty standard to say that that's really the only way that adversaries can access information about the permutation phi. And then furthermore, I'm going to model these permutations as random, which is some idealized model. It's slightly different than actual SHA-3, but is pretty standard. Okay, I'll figure it out eventually. Okay, so if you can prove some security notion in this model, then you've proven it in the random permutation model, which is sort of analogous to the random oracle model. And classically, we have really strong results. If you make classical queries to phi and phi inverse, we get basically if the internal function phi is ideal, an ideal permutation, then the sponge is as good as a random oracle in most settings. And in this work, I'll tell you about some partial progress towards getting the same post-quantum security guarantee against adversaries that can make quantum queries to these oracles. And proving this full indifferentiability result, I think, would be a big result. This is a pretty big open question because this is the basis for our belief that the sponge is a secure construction. But we don't really have many results about analyzing quantum query algorithms in this context. And really the main reason, I think, is that we don't have good techniques or modeling algorithms that can make forward and backwards queries to random permutations. Like one big kicker is we don't have a compressed oracle for this case. But even more basic quantum query techniques haven't really been applied in this model. And so for simplicity, I'm only going to talk about one round. I think beyond that, we don't know anything whatsoever quantumly. So this construction, there's just one fixed input of a fixed size, and we pad it with zeros, run it through phi, and then truncate the output. And so even though phi can be evaluated in the inverse direction, one might hope that this is a one-way function, or it has some other properties of a random oracle. Okay, and actually we know that when the top wire is like a smaller size than the bottom wire, Mark Jandry has a paper from a few years ago that says that this construction is reset indifferentiable from a random oracle, which really means it's as good as a random oracle. But a problem, according to Wikipedia, the SHA-3 standard doesn't really fall into this regime for much of the standard. And more broadly, there's not really a reason why the sponge shouldn't be secure outside of these parameter regimes. But unfortunately, reset indifferentiability is provably impossible once if the rate is any constant fraction larger than the capacity, like there's a generic attack. In the regime where we do have this indifferentiability guarantee for concrete properties like one-wayness or collision resistance, the bounds we get are only super polynomial, so they're not tight. And so anyway, the bottom line of my slide here is that we need more techniques for analyzing quantum algorithms that make ways to permutations. And so this state of affairs led UNRWA a few years ago to define this problem called double-sided zero search. And so this is just a simple natural query problem that captures some of the difficulty in analyzing the sponge. So we have a permutation that's now it's just 2 n bits. So you can kind of think of the 2 wires as being the same size. And we're just looking for an input whose last half is all zeros, that when you run through the permutation, you get an output whose last half is all zeros. And you can show that if you could efficiently find a zero pair in a random permutation, then that would immediately give an algorithm for for finding a zero preimage in the one-round sponge. And it also gives a length extension attack for finding a collision in the full sponge. So, it's not a lower bound here wouldn't give full sponge security, but it's at least related to the sponge. And so just some more intuition about what's going on with these zero pairs. So if you just pick a random permutation, this is a pseudo-random permutation on n equals 2 that I drew for you. The black dots are things that could be in zero pairs, and the gray dots are things that couldn't be. And this example has 1 zero pair, and it turns out that that's typical for random permutations. And there's going to be at least one with some constant probability. So, it's not an unfair challenge to ask an adversary to find one. But the probability that there's many falls off exponentially. So really, you can kind of think of the case to look at as there being 1 zero pair or constantly many. And then Bayesian sampling, or your favorite classical technique, tells you that you need 2 to the n queries to the permutation and its inverse to find a zero pair, if there is one. Okay, and in these papers, UNRWA conjectures that the best quantum algorithm is just the is just the trivial Grover speedup on the brute force classical algorithm. And like I was just telling you, this gives us some evidence, if it could be proven, that the sponge is post-quantum secure. And also, it's just a simple natural query problem that we should understand. And you can read UNRWA's quote from that paper if you like. And the main result I want to tell you about in our paper is how we prove this conjecture and show that the trivial Grover speedup is the best you can do for finding zero pairs when you can make 2-way queries to a permutation like this. And I'll just point out that I guess this bound is for finding zero pairs with constant probability. Our bound is tight for any success probability you like. And it's based on a certain kind of worst to average case reduction that is inspired by some group theory, which I'll get into for you. And it also leads, I told you this implies zero preimage lower bound for certain parameters, but really the same technique also gives you one wayness of a single round of the sponge for any parameters you like. And that's like a little more technically involved, but conceptually the same as the proof of zero search. So I'll just focus on this for this talk. So like I was just telling you, we'll start with the worst case instance, which I'll just get from unstructured search. And then I'll tell you how to re-randomize it in a way that kind of preserves the structure of the problem. So the worst case is a permutation where there are no zero pairs whatsoever. So this is an example of such a permutation where we just flip the last n bits. And clearly, if the input ends in many zeros, the output's not going to end in any zeros. It's going to end in all ones. But for technical reasons, actually, we're going to need a worst case instance that has k zero pairs for any k. So this is where we're going to use unstructured search. So F is some instance of unstructured search. It takes in n many bits as inputs. And on k out of 2 to the n possible inputs, it's going to output 1. And then all the rest is going to output 0. And the quantum query complexity of finding preimages of 1 in such a function is very well understood. It's been understood for like 30 years since before I was born. We know the exact constant. We know everything about this problem. So if we can reduce to it, then we're done. Okay, so the worst case instance we construct has 2 cases. And to figure out which case you're in, you're going to look at the prefix of some input, the first half. You're going to run it through F. And if the prefix is unmarked, then we're going to do the same thing we did on the last slide. We're going to flip the last n bits. And this is to ensure that any prefix that's unmarked can't participate in a zero pair because of the argument I just gave you. But if the prefix is marked, then we're going to do nothing to the last n bits. And this is to ensure that any marked prefix will appear in exactly 1 zero pair, which is just the zero pair you get by padding it with zeros. And so we have a one-to-one correspondence between zero pairs in this permutation and marked elements of F. Furthermore, the inverse queries here can't be useful because this permutation is just 1 and 2 cycles, so it's its own inverse. Okay, so it's hard to find zero pairs in this permutation. Now, to get that it's hard to find zero pairs in a random permutation, we're going to what we call symmetrize to make this a random permutation, which is, again, a pretty simple procedure. We sample 2 permutations, I'm calling omega and sigma, that both preserve the property of ending in 0 to the n. So they preserve the suffix. And then we're just going to sandwich the worst case instance by these 2 permutations. So pictorially, the symmetrizing omega and sigma, they shuffle the black dots, they shuffle the gray dots. They don't shuffle between the black and gray dots. And, we do this on both sides. Okay, and this is kind of a structured worst case instance. And if we run it through these symmetrizing permutations, it looks pretty random. Great, but how do we prove that this is actually sound? So, okay, we'll do 2 steps. First of all, I want to convince you that we can still extract marked elements of our unstructured search instance from this permutation. So it's in words there, and I'll also just explain it in pictures. So pictorially here, S is an algorithm that is trying to solve unstructured search, defined by this function F. Okay, and it's going to do that by this procedure I just told you, where we sample symmetrizing permutations and then sandwich a worst case permutation we get out of F. And note that this symmetrized permutation, we can implement forward queries and inverse queries, because sigma and omega is just, S has their full description, it can invert. And again, the worst case instance is its own inverse. So everything here is easy to invert. And then if you, I'll come back to why this is random, but for now, just believe me, then we take this interface that we've implemented and we hand it to an adversary for double-sided zero search. It solves the problem. We get this pair. And if this is a zero pair in the symmetrized phi, then the idea here is that we can undo the outer omega and sigma permutations. And the key point is they preserve the suffix 0 to the n. So this is now a zero pair. Sort of once we've unwrapped the outer permutations, it's a zero pair in the worst case instance. And by the argument I was just telling you, that's a marked element in F. Okay, final step. Why are these random permutations? So here, I'll appeal to some group theory, and I'll just sketch it. The paper has full proofs. There are only a few lines of algebra, so check them out. Don't be intimidated. But I want you to think of the permutations as being drawn from the symmetric group on 2 to the 2n elements. And then the symmetrizing permutations that we sandwich our worst case instance with, they come from a certain subgroup of the symmetric group, which is that preserves the suffix 0 to the n. And by the way, this is called the Young subgroup. Like in general, subgroups with a product structure like this are Young subgroups. And the theory here is pretty well understood. And we can apply this to our problem by this lemma that characterizes the double cosets that these subgroups induce on the full symmetric group. So I've labeled the double cosets, which are just sets of permutations that we've partitioned the symmetric group into. And we can label one C sub k if it's the set of permutations that have exactly k many zero pairs. And with this characterization, we appeal to just a standard group theoretic fact that if you have any fixed element of some double coset, so our fixed element is our worst case instance. And by the way, this is why we needed a worst case instance for every single one of these double cosets. So every single number of zero pairs. Then if we sample uniform random elements from the subgroups used to define these double cosets, we'll get a uniform random element from the double coset that is generated by this phi w. Okay, so that plus the tail bound that I told you right at the beginning, you can combine all these to get the lower bound that I claimed, which is if you make Q queries to an invertible permutation, then you find a zero pair with a probability that goes like order Q squared over 2 to the n. And a very similar argument tells you that if you're playing the one-wayness game for a single round of the sponge, and again, you have forward and backwards queries, and I'm calling the rate R here and the capacity C, then you win one-wayness, you invert with probability that goes like Q squared over 2 to the minimum of R and C, which is kind of the natural security parameter of the sponge. And both of these are tights up to this leading constant, which probably isn't tight, for any success probability you like, just by like trivial Grover attack. Okay, so going forward, we're interested in whether this idea of symmetrizing over double cosets is useful, for other things. And one place to look is just all of the other sponge properties that we're interested in. One-wayness for many rounds. We could ask about collisions. We could ask about second preimages. There's an endless list, but maybe the main goal here is showing that the sponge construction is indifferentiable from a random oracle, which would in particular, if we had it for the full construction, give all of these lower bounds that I'm telling you about for free and say it's sort of as good as a random oracle. And yeah, if you're interested in this, you should also check out some concurrent work that's very nice and gives similar results, but using sort of different techniques. That's by Mayans, Mullavolta, and Walter. So yeah, I guess these questions are in the air, and maybe in the next few years, we'll have answers. Thank you.
Thank you. We have time for one quick question you may have. Questions for the speaker? Well, if not, then let's thank the speaker again and all the speakers in this session.